Hello, everybody. My name is Jacob Huang. I'm the director of IAS. I think this is the first IAS distinguished lecture to be held in this new site, new lecture theater. So, do you like this lecture theater? Okay, thank you. We're going to have more and more lecture and conference symposium in this small and comfortable lecture theater. And today it's really honored to invite a very famous scholar, originally from US, now in Taiwan, and he's the expert in this field. If I'm right, I think you graduated from National Taiwan University, right? The same as Professor C.T. Liu. And then he got his PhD degree in applied science from Harvard University back in 1968. And from 1968 until 1993, totally 25 years, he's been serving in IBM, Washington Research Center. It's very, very famous, prestigious. And he's been there for 25 years. And all of a sudden, he feel a little bit tired. So he transferred to UCLA from 1993 until 2016 for totally 23 years. And then he retired from UCLA and become the TSMC chair professor in Taiwan, National Jiao Tong University. Jiao Tong University is very close related to our CTU. We have a very extensive collaboration. So in future, I'm sure people will see Professor Du more often. And also, he got many awards. He got he's a fellow of APS, TMS, MRS, overseas fellow of Churchill College, Cambridge University, and so on. And he was the president of MRS in 1981. Wow, so I'm sure some of people are MRS fellow or member, and he's the president. And also he received the 2013 John Boarding Award from TMS, and also IEEE Component Package and Manufacturer Technology Award in 2017. And he is a cabinet in Academy Sinica, and also he has published over 500 journal papers with very high citation, and his textbook, Electronic Thin Film Reliability, is very, very famous. Was published by Cambridge University Press in 2011, and his co-authored textbook on kinetics in narrow-scale materials is published by Wiley in 2014. I'm sure somebody used this textbook. And his research interests mostly in metal-silicon reaction, solder joint reaction, electromigration, and all the kinetics theories related to interface reactions, mostly in semiconductors. So he's very famous in this field, and also he's a very one of very good expert on 5G and AI application. So we are very, very honored to invite Professor Du to give the lecture. So let's give him very, very warm welcome.
Professor Huang, thank you for your kind introduction. Also, the invitation and arrangement for me to come. I'm so happy to be here. Distinguished faculty, students, ladies and gentlemen, my talk today will divide into three parts. First, I would like to give you an overview of the semiconductor industry at the moment, okay? And then I will talk about what is 5G, all right? And then finally, gave you example on AI, in so-called 3D IC, reliability. Okay, I will explain to you why reliability is important, and also what do we do. Okay, AI at the moment is hard, but the question, how can you cut in? And then what do you do, right? What kind of problem you solve? Anyway, so let's move ahead. First, about the recent event in semiconductor technology. First, Japan has lost its leadership. 20, 30 years ago, Fujitsu was so successful. And actually, they claim they want to buy Rockefeller Center. Oh, this makes U.S. people very upset, okay? So they try to fix it. And then they found out Fujitsu sold some device to Russia. Then U.S., take two of their top management into jail, okay? And then make sure that anything they do must tell U.S. More critically, at that time, the exchange rate between yuan and dollar double, from 200 to 1 to 100 to 1. So Japanese feel they are very rich. However, that affect their exports. So in the last 20 years, Japan just going down. Okay, I think right now they are coming back, okay, a little bit. So this is a lesson from Japan. Now, if we look at the European country, big countries, England, France, Russia, they have no presence in semiconductor technology. Reason is the following. Russia is poor because a factory to make chip is $3 to $5 billion. Okay, so Russia just don't have the money to do it. Then England and France, they are socialist country, so their budget is very even spent. They can concentrate on semiconductor because that takes a lot of money. Okay, then later Taiwan, Korea become the leadership. Okay, really leadership. Now Korea, the Samsung is heavily government support. So no matter what they do, government will put money to keep them going. Taiwan is unique. Taiwan government do not support the TSMC. Yet TSMC, they collect all the design all over the world and they make the device for you. Now, this means that they know the trend of technology because everybody tell them what they are doing so they know the mainstream. So therefore, they use the money they make to develop the leading technology like lithography, immersion lithography invented by TSMC that has lead the technology for 4, 5 generations, even up to today. So Taiwan is very unique, okay, in that case. Then everybody knows China want to catch up. However, this time the Chinese people very humble. They say, oh, probably will take 10 years, okay? Now, you wonder, how come it takes so long, right? I mean, they do so well in everything. But in this area, if you want, I can explain to you a little bit later, okay? But China, this is important. China want to catch up, okay, and then to do that. Also, we know at the moment, U.S.-China trade was really about advanced semiconductor technology. If who control, lead the technology, they make all the money, okay? The rest is not important. At the same time, I will explain to you later on, Moore's law on miniaturization in silicon transistor is ending or come to a war, okay, has to stop. Now, that has a big impact. So China may be able to catch up because, if you can move ahead, I can catch up easily. no doubt, 5G AI here, these affect our society and everywhere, okay? So this is my talk today, okay, about that. Then, today you have cell phone, right? This means that future, this will act as your sixth sense. Okay, if you know Chinese, although you know these are. So today, we can see, we can hear things miles away, all right? And the difference are how clear, how good, there's difference are. But this, we are able to do that, all right? And no doubt. And then cell phone, everybody has cell phone, but means that cell phone today is a computer now, medium-sized computer. So everyone is carrying a computer with you. So we can do a lot of things. That makes the difference, okay? That, so to speak, changing our society, okay? Now, on society advancement, then let me quickly review. Civilization, all right, and advancement, we know in 18th century, the invention of steam engine led to industrial revolution. What it means is that machine power replaced animal power, okay? So that's what it means, basically, okay? And then machine production, these change everything. Feudal society to democratic society, then unfortunately, capitalism come in, and then communism come in, okay? And then socialism eventually, okay, in Europe. Now, that has affected our history for 200 years, okay, very big effect, okay, due to this invention of that. However, today, because invention transistor, also very large integration transistor, because you need that, okay, then lead to, right now, intelligent revolution, okay, yeah, intelligence, artificial intelligence like that. What it means, transistor, is that data power enhance machine power. Machine power is already power, but adding data power, wow, robot can do work for us, okay. No doubt, robot up to now is already replaced worker, right? Let me assure you, in the near future, robot will replace professional people, expert, okay? We will see, okay? So our society changing very, very rapidly. Then the questions are sustainability, okay? How can you sustain your growth, whatever, of your society? Now, the first trend, everybody knows, sustain energy consumption, all right? Sun, solar cell power, environmental protection, right? Temperature too hot, whatever like that. And then we need green energy technology and also waste management. Waste means that nuclear waste, okay? How do you manage that? Very important, okay? Otherwise, deep trouble. But people may not appreciate this. The second very important trend is Moore's Law. Why Moore's Law we talk about? Yeah, because it has sustained the growth of microelectronic product for over 40 years. In human history, nothing has done that, okay? This is a 40 years growth. Now, Apple, Amazon, market value over $1 trillion. The old company like IBM, Exxon, GE, we don't mention that at all, okay? The big company today is this kind of company. But the question, at this size, how can you sustain the future growth? Okay, this also we need to ask that, all right? And then let's begin to talk about 5G. 5G is a communication, all right? In human history, the process in communication starting from language, written words, all right, no doubt, printing, because that Bibles are available, books are available, so education become popular. But printing Bibles is a very important event, okay? So printing available. Then telephone, okay, wire or wireless, okay? We can pick a phone, call your friend, okay, like that, okay? Now, after that, television, because picture image is communicate to every home. Then internet comes in. What does internet mean? Internet means a computer-to-computer communication. Before we are phone to phone, right? So internet is computer to computer, all right? Then later on, cell phone to cell phone, so mobile computer to mobile computer. So therefore, at home, every children, lady, wife, they all have a cell phone. Okay, wow, these communications everywhere. So we are today, okay, and here. And then let me recall .com. This late 1990. In Hong Kong, some of you might remember Li Jiacheng, the son, want to form a .com company, okay, but it didn't work out, failed, okay, because even though we have computer, but not movable. Only until so-called cell phone become popular, we can make cell phone become popular, is we can make cell phone now, mobile phone. Then you see now Apple, Microsoft, Amazon, Facebook, these are big company, okay? And then these change everything, okay? So now you see .com was not successful because not mobile, okay? You need mobile technology. So let's come to 5G, okay? What is 5G? 5G means advanced communication technology, which combines hardware and software. Okay? Hardware, there are satellite, optical fiber, server, big computer, base station. Please remember these are very important. Huawei is good at this, okay? I'll come back to that. Mobile device, sensor in terminals, okay? So you need all these hardware to make 5G or whatever available. Now, software, operating system, like Andre, like that, okay? So this is yeah. So I won't talk much about that, okay? Yeah. And this enable us to all kinds of intelligent work. 5G, 4G has changed our daily life. 5G will change our society, everything. Politics, economy, art and literature, health system, agriculture, industry, military, okay? And I will explain a little bit because you heard all national security reason. U.S. want to so-called control Huawei, whatever. Military reasons is very important. So why, okay? Now, I have to show you this picture, okay? This was in 2014, okay, 5 years ago. The U.S. industry already agreed that by 2020, 5G is going to replace 4G. On the other hand, in China, Huawei knows this, so they make announcement 1 year ahead of everybody. Oh, they make everybody very mad, okay? U.S. government, U.S. industry very mad because, you don't follow the rule, okay? You take advantage of 1 year, and that's why Huawei is in trouble. One of the reasons, okay, Huawei is in trouble. Now, what does 4G and 5G mean? These are the flower, the pedal, 6 pedal means 6 functionality, okay? For example, these are end-to-end latency, okay? I will explain that. Latency means that you send a signal out, how fast they come back, okay? You think about you drive a car, the car in front brake, you have to be able to stop within that time. So these are very short time, millisecond now, okay? this like mobility, okay, connection. The connection very important, okay. The data rate, volume, density, like that. So the yellow flower means 4G, okay. You are here, 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 here. 5G means that you are here, 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 here. So some of you, young student, you should walk 6G, right? You've already 5G, so I want to walk 6G. Means that, yeah, you go over here, you go over here, like that, okay? So it may not be that easy, but I will explain to you later, okay? But clearly, this is the 5G picture, okay? So these are well-known. If you have disability and your product can do that, yeah. Also, the spectrum efficiency, the wavelengths, this we'll talk about that. Yeah, this milliwave, okay. Energy efficiency, cost too, okay. Cost too. So these, I have to say, these already announced 5 years ago. So everybody tried to follow that. Huawei did not. So this make everybody upset, okay, yeah. All right. Why 5G affect national security? Okay, because data signals very important. It can be transmitted via air, via underground, via land. Okay, air by satellite. Okay, no doubt. But during the war, first thing happened, I shut down your satellite. Okay, this is very clear. Okay, so therefore, satellite is not reliable. Okay, you must have backup. Then we go underground, all right, by optical fiber lines, okay. I may just comment, China, building one way, one bill, okay. Trust me, along the railroad, whatever, there's optical fiber, okay. Going with the railroad, okay, because you need data, you need information like that. So, but to make optical fiber, okay, require rare earth. Because rare earth doping in the big energy gap, provide so optical resistance, lower resistance, so the optical wave can propagate a long way. You need rare earth, and you need a lot of optical lines. So that's why rare earth become a strategic material. Because, you hear all the time, right? Why? Because fiber depend on that. Now, then also on the land surface, you need to build the base station, okay? You can see, this base station. Particularly in a country like has big land, China, Brazil, okay, Russia, even Italy, they need to build a lot of this base station. But base station costly, except Huawei. Huawei can build very good, very cheap. That Huawei, you can't beat him, okay? So that's Huawei. Huawei will do very well because they do well on the base station. Even their cell phone, computer, they don't forget. Space station, okay, it's a very important element in 5G. That's why in China, every signal go to rural country, whatever like that, okay? Now, for example, why this optical fiber important? This news about, I think I cut from the paper in Taiwan a few weeks ago. Los Angeles to Hong Kong, the optical fiber under the sea probably will be stopped. Okay, obvious, if a signal come to Hong Kong, will go to China quickly, right? So you cannot have that. Okay, so that's why you can see the national security issue very relevant. Now, then let's come back to talk about the 5G capability requirement. Yeah. I hope some of you can understand Chinese. These probably make it very clear to you, okay? First, end-to-end latency. These require millisecond, okay? These are very important in so-called humorless card, okay? And the card, LiDAR, okay, must be able to detect signal, anything come out, reflection, right away, you have to brake. Otherwise, you get accident, okay? Now, peak data rate, mobility, yeah, no doubt, yeah, you need that. Volume, yeah, transmit large volume because image, all these things, you need large volume, okay? That's the connection station because everywhere my network is available, okay, available. Yeah. And then in everything is connected, okay? And then also energy efficiency. Your battery, you cannot use too much energy, so therefore low power device operation become very important. The secondary requirement is it has to be security, reliability, okay, reliable, and then low cost. Okay, so these are the 5G requirement. I mean, the limit, as I showed the flower petal, okay, and are here, okay. Then, yeah, let's quickly talk about end-to-end latency. So instant response, it depends on time of flight. On a humanless vehicle, the LiDAR, not radar, LiDAR, okay, on top, the car requires feedback time of a few milliseconds in order to avoid accident. If you don't have fast latency, then accident will happen, okay? In a chain of car, for example, if the leading car stops suddenly, the time gap to respond for all the car behind is only about a few milliseconds. So that's why latency is very important, okay, requirement. The signal come out, reflect back, okay? It's not just one way, okay, yes, feedback. Density connection. China already about 600 these 10 to the 4 base station now, this one, okay, yeah. Now, even rural village have base stations, so cell phone can be used everywhere. In China, you don't need to carry cash. You can pay by cell phone in no man's store, okay? So you can make connection to almost everything, especially your home, where artificial devices are implanted, okay, yeah. So connection. For example, people talk about 3C, okay? You need connection, you need collection data, connection, and then computation. So these will enable you to go from 5G to AI like that, okay? So this is one of the very important connection requirement. Then signal. Before like a double twice, today is 1,000 times per year. Like this, we're talking about a lot of signal over us. Okay. Then volume important. Download is very fast than upload. Okay. So download a book, movie is no problem. Instant, more or less instant now. Yeah. With a high traffic volume, density transfer, image will be much clearer, with much better resolution, okay? Same as music. So you want to hear very nice music, see very detailed picture, you need that kind of capability. We have instant news and weather report, okay? Yeah, very important. Then Internet of Things, basically, we have man-to-man, man-to-machine, machine-to-machine connection. So everything, okay, everything like that, yeah. This Internet of Things, okay. And mobile Internet. Now, this picture too busy. I just mentioned that. In the future, a soldier just carry two things, weapon and Internet. That's all, okay? So, because before, okay, communication is very important, right? No, in the future, every soldier has a communication ability. So this is a change. Sorry. Now, let's come to the frequency, okay? Again, sorry, I cut this from Taiwan newspaper. They are trying to so-called sell this frequency. Now, this is 30 billion Taiwan dollar, like 1 billion US dollar. 1 billion is quite a lot of money, okay? So company have to buy this, okay, in order to use that. So you see these wavelengths are a very important issue. Now, if I go a little bit more, just shows that at the moment, for 5G, there are two kinds of frequency you can use, okay. First is called sub-6. These are about 3 to 4 gigahertz. It's a low frequency and long wavelength, okay. But advantage, the interference is less, okay, refraction, diffraction less. Now, the higher frequency is so-called 20 to 300 gigahertz, called millimeter wave, okay? And but it can carry more information, but more interference due to scattering, okay? While in China using the low frequency, okay? But US military is also using low frequency. That means that US industry have used a high frequency because you cannot overlap with the military. Now, this a issue means that your loss is you have to have more base station because your interference is high. You get more higher cost, okay, and so. Things will clear next year, okay, what happened in US, okay, or rest of the world. Now, you may here ask a question, how about 6G, right? 6G, let's go to below millimeter wave. Then you go to microwave. Microwave, you're kidding. Microwave, you can cook water, right? You can cook things. So therefore, beyond this, how it will happen, I don't know. I'm not expert here, so I think you need to talk to EE people. They can worry about that. But this is going to be an issue in the future, okay? So you don't have millimeter wave for now. You need to go to microwave. You're kidding, okay? All right, then let's come to Moore's law, okay? Everybody knows Moore's law, but I want to make it a little bit more clear to you, okay? Moore's law means that on chip, on a silicon chip, transistor density double every 18, 24 months. That's Moore's prediction, okay? Indeed, it's true. However, what didn't tell you is that you can double, but you cannot double the cost. You have to keep the cost the same. Then transistor becomes cheaper, right? You double density, you don't make increase cost, so become cheaper. So that's why transistor cheaper and cheaper, okay? Indeed, on this curve, you can see from 1970 to 1985, 1K, okay, per chip circuit to 1 amp, okay, about 15 years. Okay, then from 85 to 05, 20 years, you go from 1 amp to 1 G. Okay, 6 order increase, okay, and then the cost of transistor 6 order cheaper, okay, and now, then I'd like to make it clear the two most important contributions of Moore's law. It enables the development of mobile technology because of physical size reduction. Because you make things smaller, size becomes smaller. So mobile technology can be done. Okay, I will show you later. The cost transistor is dirt cheap. Because density reduction without cost increase. So today, just like dirt, okay? So very, very cheap. This is also a problem with China. how can you compete with dirt, right? So now, the physical size reduction, let me show you these. These are 2002. These are medium-sized computer. This is a block, like a little bigger than my hand. So these are 2002, okay? Now, you don't see the transistor because on this pink block, between the pink block and the back, there are 10 by 11, 110 transistor chip on this block, okay? Now, this is about $250,000 computer at that time, okay? And now, if, say, like 10 years later, if we can replace 110 chip by one chip, no problem, we can do that, okay, indeed. This is more slow. Then we can make things mobile now. You see, this is not mobile, right? This is a big piece computer on your desk, okay, whatever like that, okay? But if I can replace 110 chip by one chip, then this chip I can put in a cell phone. Also provide that you need to with a keyboard by finger touching, okay, this, so that you're able to send signal, whatever like that. So physically, these people may not appreciate it, but it's very important. So now we have a mobile technology because of Moore's law, all right? Then cost, okay, as I mentioned there, cost, okay, keep going down, 6 order, like that, okay, this way beyond. So today, if you make calculation, the cost producing one transistor is cheaper than you print a alphabet in your newspaper. Very simple. If you go to buy a book, you have to pay, I don't know, 100 Hong Kong dollar like that. I can push a button, send a book without cost. All right. So this means that the transistor is dirt cheap, but we need that. Okay. Yeah, you need that because you make a lot of cell phone application. The transistor has to be cheap. Okay. Yeah. Otherwise, things will not be available to us. The cost per transistor is cheaper than the printing of alphabet on a newspaper. The problem in China is this. Okay, how China can make everything cheap except transistor. Except transistor. So problem in China, how to make transistor cheaper than those made in US, Taiwan, and Korea. Okay? They may take 10 years to do that. Okay, and yeah, we'll see. Okay. The problem in U.S. is how to find new and huge application in order to use up all the extremely large amount of transistors they make. You make so much dirt, you have to use them up. That's why cell phone, it's everywhere, right? Use a lot of memory, logic chip, okay? Then, after mobile consumer electronic product, new invention, people say in biomedical application will be critical in the future use of transistor. So these are not my point, more people agree. The future of most important technology is how to combine microelectronics and medical application. Yeah, because people getting older, so you will need that, okay? Yeah. So aging problem, right? These sorry, I just say Japan, okay? Even Taiwan is also had the same problem, okay? People getting older. Now, older means that you get sick more easily. If nothing else, you are diabetic, okay, big problem. So, for example, vital data health, body temperature, heartbeat, blood pressure. Today, you hold your cell phone. all these can be recorded, okay? But then, if you have diabetic, we have to use an invasive method. Oh, need to put a drop blood to do the test. Nobody like that. So therefore, very important, we need non-invasive method to detect them, okay? Because urine, mouth water has low oxygen content. You have to do the test in blood, okay? Yeah, blood, okay. Oxygen content, sugar content has to come out from the blood. So the link between microelectronics in biomedical application will be the most important technology advance in the future. Okay, so this is that's why a couple of weeks ago in a meeting between National Jiao Tong University and TSMC in Taiwan, the CEO of TSMC, not 张忠谋魏基家, he said, transistor technology will have 30 years to go. So therefore, this field still a lot of future. So because society need is there. So at least 30 years more. Okay. Now, I have talked about the transistor 5G. So let's come to AI. Okay. AI. All right. What is AI? Okay. I cannot move now. Can you help? Yeah. Thank you. I give you a very simple example. Okay, toilet. Sorry, because you understand that. Okay, toilet. Okay. Now, automatic toilet is very popular in Japan. Okay, they like that. The seat cover toilet can be warm, and the nozzle can spread water clean you afterward. Okay, beautiful. But it performs a predetermined set of functions. Okay, so 3G, 5G technology will do that. Just like in the factory, the arm, okay, match arm doing this, doing that, fixed function. Okay, they can do. However, an intelligent toilet, what does that mean? An intelligent toilet can recognize that you stand in front of it. If you face it, it will open two covers. But if you back face it, you will open one cover. Very simple, intelligent, okay? They can do that, okay? So, sure, more than that, after you finish urine, the sensor in the toilet can detect sugar content, diabetic, or acid content, gout, okay? Very serious, so do that. And then, you're normal, they will not do anything. But you're going up, they will send an email to your doctor. Oh. Okay, so this can be done, okay? So the toilet can make a right decision. You will take 5G technology to do that. Even very simple, okay? This is a very simple, intelligent study, okay? All right, then let's more serious about AI application in mobile consumer electronic product. Why I picked this topic is because it's a rapid growing industry for 5G technology. Okay, this growing very rapid. Low cost consumption, battery limit, small form factor. Yeah, if you're too big, a young lady will not be able to have it. Okay, so it has to form factor small and multi-functionality. Okay, has to be that. Heterogeneous integration because you need complementary MOS and photonic chip, whatever like that. Then we come to three-dimensional integrated circuit. Okay, so what 3D will explain? Again, can AI help improve reliability in CD? So this is the question. Okay, question. Now, why 3D? Okay, this picture 2D. Okay, so things are arranged on a surface. Okay, but this takes a lot of area. So then we stack them. okay, stack them. So for example, here to here, long, but I go that short, okay. So there's a lot advantage to go 3D, okay, because save power, save volume time. Then this is schematic diagram, we call it. Don't take it seriously, okay? These are from your development. Means that you need to see these are PCB board, these BG laminate, okay? Important thing is that there's a interposer, silicon interposer between the substrate and the CPU and the IC, okay? The reason is this, because the silicon interposer thermal expansion coefficient is same as the silicon chip. So therefore, there's no stress there, okay? Otherwise, there's a big stress problem. That's why these interposer or 2.5D interposer. 2.5D means that on this interposer, there's no transistor. If you put transistor, because silicon you can put transistor, then it becomes 3D, okay? Now, this was a big problem between Taiwan, the TSMC and other packaging company, okay? So, so this is so-called new, okay? So with the TSV, these a lot of new technology here, okay? Even though these are known more than 10 years ago, but we don't have production yet because the cost to do this too high, okay? Problem too high. Then let me show you the real thing. This is a 1 centimeter long. This is a chip from Qualcomm, okay? Our student put in a hairpin, hold it, and then polishing it. And so we can study the structure. And then we took the sample to synchrotron radiation at the Lawrence Berkeley National Lab, okay? And then you can see the 3 layers of solid ball, okay? I think if you, sorry, let me go back. Yeah, you can see 3 layers solid ball, 1 layer this ball, 1 layer this ball, 1 layer this ball, okay? And then, yeah. The blue are the copper link, okay, copper connection. But you don't see silicon chip, you don't see the polymer because the absorption too low. So you don't show in the X-ray image. Now, how to inspect a 3D structure because these are deep inside, okay, so let me explain that by giving you example. We use X-ray to inspect our lung for cancer or tuberculosis. If you have a back spot, okay, you take an X-ray picture, but there is 2D projection. Anyway, the doctor, if he's experienced, he can tell you whether you have a cancer there or you just a tuberculosis, okay? So means that to inspect internal structure of a 3D IC, we need X-ray tomography or X-ray graphic processing unit. You know graphic processing unit, right? These are recognize your face, right? But internally, then you need to go in by X-ray, so-called X-ray GPU. For machine learning of the tomography, we use synchrotron radiation facility or tabletop X-ray machine with high resolution, okay? Now, synchrotron radiation problem is that they don't give you much time. So we only got like a week or 2 weeks per year. However, we need help from so-called Dr. Xie, okay, Xie Yongfen, MacTech in Hsinchu. They have a tabletop X-ray. They can take very good 3D imaging, okay, like this structure. This imaging can rotate 360 degrees. So therefore, you can inspect the structure any problem or not. Okay, for example, next one, they say watch. Okay, yeah, this you can turn around, you can see the structure very clearly. Then, for example, a little more detail, say Kelvin probe. Okay, like here. So, for example, you can pass current from here, go up here, and then go out here. Okay. Then you can measure voltage from here, here. So you can measure IV, and then if this Kelvin probe fail, then we can see that very clearly. Okay. For example, again, for some reason, yeah. So, okay, then we want to do the reliability. What is the purpose, goal of reliability? Two of them. First, to find weak link or early failure in the system. These are so-called unacceptable or abnormal failure. We need to get rid of them. Okay, these are abnormal. These are no. Okay. Then second, we have determined the mean time to failure, MTTF. These are acceptable or normal failure. Okay, this kind of failure is you have to have that. Okay, this is your device. If you fail within this, okay. But if you fail early, you have weak link, no good. You need to get rid of them. Okay, so the reliability test, that means typically accelerator test. We need to pass current as a function of current density, time, temperature to induce failure. Then we have large set of this failure data. Then we obtain a distribution function. So, like AI, you need to collect a lot of data, right? Yeah, big data. This, we are doing that too, okay? Distribution, okay? And then from there, we obtain the mean time to failure, okay? Then because failure takes time, so it means the diffusion, this kind of thing, is a kinetic problem, okay? So activation energy has to be, for example, this again, this is a picture from Qualcomm. So again, you can see from one of BGA cathode. Okay, we pass current, go up, and then go through these many microbump, and then come out from the other end, like that. Now, if I pass high current for a long time, it will fail, no doubt. Okay. Somewhere it will burn or whatever like that. Then we will be able to find out is there weak link or normal failure like that. Okay. For example, this example, there are 36 microbump. Okay, microbump. After we pass current until they fail, all right, you see this guy here looks different. Looks different from the rest. The rest are normal. Okay, this one failed. And then we can do cross-section, and then you see, indeed. So this is a before fail, this is after fail. So therefore, we see, this one is bad. So therefore, we need to compare the picture before they fail to see, what is wrong with this bump? Okay, maybe the manufacturing, there's a weak link there. Okay, so then, my talk, no question, no equation up to now, right? So I have to show one equation, right? So these are so-called empirical equation, Bragg equation, mean time to failure, current dependence, activation energy. Okay, so then you're interested in that. Sorry, I invite you to. We just published a paper. Okay, we have unified model for mean time to failure for electromigration, thermal migration, stretch migration, based on entropy production. Okay, so you're interested in that, Please take a look. Okay. Now, this is so-called the distribution function. Okay, we make this failure, and then we take the 50 middle. So this is the mean time to failure. Okay, this 50 failure come down to time. Okay, so we can obtain that. So this indeed quite tedious, quite time-consuming study. Okay, and the goal of our AI is this: in the future, when a new device is in production, we examine by X-ray GPU, and we can identify quickly the weak link where anything occurs. Mean time to failure, in the future, you don't need to do all the time-dependent, time-consuming reliability tests, okay, one by one. And AI, hopefully, provide time-independent reliability. Oh, you ask, okay, what can AI do for you? Without AI, we have to time-consuming study. Past current, time, temperature, lot of study. Now, if my machine learn a lot of failure already, so the machine is better than a professor, okay? So when you take a picture, the machine can compare to what was done before, tell you, hey, you have problem here, okay? And then I can tell you more or less your mean time to failure, what it will be. Sure, you can do a test and confirm that. So the AI, the goal is very clear here, okay? We convert time-dependent study to a time-independent study, okay? And so summary, finally, now 5 technology will affect our society. AI application is here. The last one is for the students, okay? Now, a lot of students say, hey, I want to study AI, I want to go to this, that. Trust me. More important, if your basic training in mathematics, physics, chemistry, biology, Chinese, English, you're good at that, AI is no issue. 3 months, 5 months, you can get in, okay? So back to the basic, okay? Physics, chemistry, math, still important, all right? Thank you, yeah. I'll stop here, all right.
Thank you, President. Any question?
Yes. Yes. Was a very interesting talk. I have a question. You mentioned that Taiwan and Korea right now take the leadership of IC manufacturing.
Yeah.
I have a slightly different point of view on this.
Good, yeah.
You have here the news that Japan has set the export restriction to 3 critical materials. And Samsung almost died. They jump out from their hot pot.
Yeah.
And also this IC industry really.
I can explain that. Okay, go ahead. Yeah.
Yes, IC industry really strongly rely on the manufacturer equipment.
Yeah.
6 of them is 6 of big one, like Prime Material Land Research in America, and 3 of them in Japan, 1 in Dutch. Yeah. And they are all American plant. So this would be really difficult for China to get out.
Sure. Your last comment, I don't want to follow, but let me explain to you. Japan has gave up semiconductor industry, even though their materials, chemistry, they control. Now, one example. What they control is the etching. One of them is etching solution, HF solution. Oh, we know that, right? HF, etching silicon or oxide like that. But what we cannot compete Japan is that the purity of HF solution Japan is leading everybody. Korean cannot do that. So if you etching with a little bit dirty solution, you leave some impurity in your device, you're done. You're failed. That's why Korea is so upset, okay? Now they are trying to learn how to make pure HF solution, okay? As simple as that, okay? Indeed, I think that's why, if you don't mind, let me follow you, make a comment. China is going to have a similar problem, okay? Now, on the other hand, you have to admit, what's new is semiconductor technology, textbook, review paper, everywhere. China has some very outstanding physicists, double engineer, graduate student. They know everything. But they cannot make it. Why? I give you example. Say at home, say your daughter want to learn violin, okay? And then you invite best teacher to tell her all the trick, how to do them. She knows all the trick. Do you think she will be able to do very well right away? No. She has to practice like 8 to 10 years to get the experience. It is experience. Like you can copy, you can steal my technology, but you can steal my experience, okay? I think what China needs 8, 10 years is to develop the experience. It's very simple. So I think all the problem you talk, yes, China have to overcome that. In summary, just it's experience that you have to have. You don't have experience, no problem. Then you will have to build up slowly, just like your kid want to learn violin like that. Okay, I don't know. you may have different comment, but feel free. Any question, please?
But they still need a machine to manufacture all this IC.
Yeah.
So
So that base is very broad, okay, indeed. So it's not, but China has money. By all means, what I can buy, okay, but experience you cannot buy. Put it this way, Machine, whatever they can buy, okay, yeah. Okay, question.
I have a question. I'm a financer, and I want to know, what is the opportunity in the investment of 5G and the AI technology?
You mean financial opportunity in 5G? A lot. Because you see, if you want to make things, you have to sell. That's where the money coming from. So you have to invest your money correctly. On the right 5G, you invest wrong, you lose money. That I cannot help you. Okay. No, there's a lot of money is very important here. You have no money. Russia, what can they do? They got a lot of very outstanding scientists like that. They cannot do anything because they have no money. So money is very important.
But how much?
How much?
A lot of money. How much?
The more the better. No, I mean we are talking about $1 billion. No.
You said 5B, right? In the beginning, you said.
Yeah. For example, you see, all this 5G AI behind depend on semiconductor technology, right? So you need the transistor to do all the things. But each foundry, $3 to $5 billion US. So you have to have a few of them. So there's a lot of money.
12 inch. If we go to the next 18 inch, that's a different story.
Oh no, that's a different story. No, this I don't think they will go to 18. They are not crazy. It's still 12. They make 2, they're cheaper than you make 1, okay, 18. 2 12-inch wafer. No, you go to TSMC, I saw the 8-inch wafer, blank wafer, just display there. They don't go ahead to make it, yeah.
But China is buying the experience from Taiwan by recruiting quite a few high-tech people.
You want to, come on, you be careful. You want to invade Taiwan? You want to bring the whole TSMC people and all the equipment to China? I don't think so. China won't let you do that. Now, you may hire like 100 TSMC engineer to China. Not enough. Not enough. You only have part of it. So you need the whole thing. That's not easy. I don't worry about that, yeah. A question, yeah, please.
Now, when it comes to applications of 5G, there have been a lot of problems concerning the infrastructure. Because you need short-range antennas.
Yeah.
And you have a huge country like China.
Yeah.
You need an enormous investment to really make it work.
That's my...
It takes a long time to work.
Yeah.
It's also sensitive.
Yeah.
To destruction.
Yeah.
I mean, what do you do in a war?
Yeah.
You can very easily destroy the 5G structure.
Right.
Whereas the 4G structure is still stable.
Exactly.
So I think we must have both.
You have good point because that's why Huawei, they build a lot of base station in China. And you need that, okay? If you can afford to do that, and then during war, they bomb you, and then, yes, these are, so it's national security concern, okay, this indeed, yeah. Not so trivial, yeah. Yeah, please.
You spoke about the U.S.-China basically technology war, with the military aspect. So where do you see this could go? Would it split the world into 2 camps that don't talk to each other? Do you have a scenario in mind?
No, sorry, I would not be able to answer your question. These are too big for me. I'm not a politician, okay? Yeah, I don't think we'll divide into 2 camps like that. No, I don't think so. This will slow down the progress, okay? And just that how much each side willing to give up, Hopefully, the talk will resume. Hopefully they can make progress, okay? Yeah. I don't think this kind of trade war is helpful, not to China, not to U.S., okay? Not to U.S., yeah.
I want to ask, have you heard about heterogeneous integration?
Even louder.
So what do you think the difference between the heterogeneous integration compared to the 3D IC?
Oh, it is more or less the same because 3D you also need to have heterogeneous integration. So you need that. I don't mean 3D is a pure just silicon technology. No. This have to heterogeneous integration is very important. Yeah. Depend on your application too. Okay. Yeah. I mean, like a communist. This transmission is 3-5 compound. All right. So therefore, don't forget about that. Just that 3-5 technology is not as advanced as silicon technology. So it's easy to catch up, easy to duplicate, okay? But silicon technology is really so-called nanotechnology to the end. So it's nanotechnology, okay? Silicon technology, nanotechnology. So that's very, very difficult, yeah.
And the resolution of the X-ray can resolve those nanoscale features?
Resolution. I don't know how to answer your question, but I can tell you TSMC is announced next year maybe 5 nanometer device will come out. Okay, so but that does not mean the physical dimension is a 5 nanometer, but the capability equivalent to that. So these detail. Sorry, I cannot answer you. I'm not expert in that. Okay. Oh, very good. Please.
Thanks for an interesting talk. I was a little bit intrigued about the part that you were talking about AI and reliability testing. And you were talking about determining mean times to failure, and that maybe we don't have to do these very expensive, time-consuming tests. But the way I understood it, and I'm probably wrong, is that if you do these tests, we only do a few, so we only have very few data points, right? And how can we have AI do that for us while we only have maybe 10 samples we tested?
Yes.
We need a lot of data.
You need. I mentioned that your big data, so it's collecting big data. So I only mentioned these tests a few, but we keep doing that. We're just in the beginning. We may have to 2-3 years. So to speak, I can compare to that. For example, if in the hospital I train a machine to learn this X-ray image, you need to take like a few thousand people. Those data then are maybe the machine able to do the first diagnosis. Okay, then the outcome hopefully checked by the real doctor to say, okay, good or bad. The key point is the following. Please appreciate that. A doctor, like a professor, you can train a few students, only a few. But if I train a machine, like able to do 90%, 95% of the work, I can copy and make 100 of them. That's a big difference. So therefore, I can send this machine to a lot of rural country. Then any patient, the machine examine them, and then if serious, send back to the real doctor to check it. So that is the advantage, that when the machine is available, you can duplicate 100, 200 of them. But human student cannot do that. Yeah.
I think, yeah, because we need to start our dinner and let all the guests go away before 7:30 because the materials close at 8. Yeah, so I think you can see all the students are gone because they think all the class after 4:30 is disappeared. Yeah, so that's why we have about 200 registration, but we only show about 1/2. So that's really pity. I think it's a very interesting talk, and this PowerPoint will be shown on our website.
Yeah.
But feel free to download it.
Yeah.
Usually we have the thousands, millions to download from students from in China. So I think, yeah, feel free to download the video, the PowerPoint. And finally, I think we want to thank Professor Tu by presenting a gift from IAS. So, do we just right here?
Wow, look at that.
Oh, okay.